Okay, so up until this point, we should all be familiar with how to use numbers such as solving for x. So let's use the example 4x plus 2 equals 18. So in this case, we should already know to subtract 2 on both sides to get 4x equals 16 and divide by 4 to get x equals 4. Okay, that's pretty straightforward, but this really isn't what we were meant to do today. But as a matter of fact, let's not even go there at all. What we're going to be talking about should answer the question, what the heck are limits? How do these differ from just a normal expression like 4x plus 2 equals 18? How is that different? Well, there's two key components to understand about limits. The first one is that with the limit, we no longer need the answer. And it's contingent based off of our second point, which is also very important and is actually the very definition of what the limit is. And really, there's just one single question that limits seek to answer, and that is, what happens to our answer as x approaches a number? Now though, while it might sound similar to just saying a simple equals and then a number, such as we had 18 last time, and that's how we got x equals 4, that is simply not how limits work. In fact, let me go ahead and add a limit right here. Okay, limit as x approaches 6 of 4x plus 2. Now, as opposed to having a number and solving for x, here what we're trying to ask is really a theoretical question. What happens to our answer as x approaches, this is a key word, instead of a number, let's say 6, just like we had in our limit here. Okay, now in this problem, it's pretty easy, okay? We can literally just plug in x equals 6, and we get
4 times 6 plus 2.
And following order of operations, we get 26. Okay, this answer, very spot on, very easy, very simple. But what if we were asked to find the limit as x approaches 5 of x squared minus 25 over x minus 5? Now, most people would say, okay, well, let's plug in the 5 here. We get
5 squared minus 25 over 5 minus 5.
What does that give us? Well, 5 squared is 25, minus 25 is 0 over 5 minus 5. Now this is a problem, because what do we have here? 0 over 0. And this right here is a massive problem. We cannot have this. The denominator cannot equal 0. And this is why the question that limits ask is vastly different than just simply saying equals. Because instead of saying that this function equals a number, what we're trying to ask is what happens to the function as x approaches a number. You see, it's a very different concept, and they answer, although they can be the same. They can be the same. We must remember that they are not always the same. When it comes to trying to solve limits, there's 3 ways we can try to attack it. Number 1, of course, is algebraically. This we will absolutely cover in the future, but right now it is not relevant to what we're trying to talk about today. The second is graphically. And essentially what this means is if I have a graph, and on this graph is a function, I can explicitly point out specific points that our limit approaches as it approaches from the right and the left. And the other way that we're going to look at today is with tables. So the ideas to tables are pretty simple. If I have an x and a corresponding y output, and I'm trying to find some limit as x approaches a number. Essentially what I'm going to do is I'm going to plug in values of x and simply analyzing what happens to our y values as our x gets more and more precise down the table. So let's take a look of how we can graphically solve for the limits. And let's suppose we have the function f of x equals 1/2 x. That would be our red line right there. Now here's the kicker. What would I be asking if I said limit as x approaches 7 of 1/2 x? What am I asking in this particular instance? Well, heading over to our graph, x equals 7 is right here. And if we just go straight up, we get this point on our graph. Now, what is the y value approaching as x equals 7? Our y value equals 3 1/2. So the answer to our problem, limit as x approaches 7 of 1/2 x, equals 7/2 or 3 1/2. Because as you can clearly see, as our x approaches 7, and this also happens in both directions, mind you, our y value approaches 3 1/2. And this is the crux. This is what the idea of limits is trying to convey. Not what does it equal, but rather what is it approaching. So what about the example I used earlier? Our function was
x squared minus 25 over x minus 5.
Okay, we know that by plugging in x equals 5, our answer becomes 0 over 0. And again, this is not good. We want to avoid this at all costs. But remember, in a limit, we're not asking what does it equal, we're asking what does it approach. Limit as x approaches 5 of our function. Now the function in question looks a little bit like this. Editor's note here. The graph that you see right here is actually not quite the right graph. That would be x squared minus 25 over x plus 5. That was a little mistake I made. If you want to see what I mean, let me know down in the comments below. I'd be happy to make another video on it. Anyways, back to what I was saying. But again, herein lies the problem. In this particular case, our answer does not exist. As you can clearly see in our line, there is an empty gap right there. So we cannot say that x equals 5. So in a normal situation, we cannot say that y equals 0. That is not true. However, in the limit, it gives us a little bit more leeway. Why? Because instead of saying what does y equal, what we're asking is what does y equal as x approaches 5. This is the key word. We're not looking for x equals 5. We're looking for x approaches 5. Very different concepts. So I would just ask this for you. What does it look like as x approaches 5 from either side? What does it look like our y value is approaching? In this particular instance, the limit as x approaches 5 of our function f of x equals 0. And that's because it's approaching 0, not that it is 0. And see, just small differences in wording like that, especially in a subject like math, makes all the difference. Suppose I have a function, 2x squared plus 3x plus 7. What if I were to ask you, what is the limit as x approaches 2.5? What would be your response? Now the great thing about tables is that we can use tables as a much more precise way to measure the limit. Now there's still disadvantages, and really the best way is algebraically. But for now, this does a lot better than just looking at a graph. And we're gonna find the outputs for a few values. At x equals 2, x equals 2.4,
X equals 2.49, X equals 2.499, and lastly, X equals 2.4999.
And if you're at all familiar with this setup, it's literally all we're trying to do is figure out what output do we get for each value. All right, let's go ahead and see what do we get if we plug in x equals 2. So we know that f of 2 equals 21. Now, let's see again, but for x equals 2.4. And so f of 2.4 is 25.72. And quite literally, we just solve for the rest. And so, it's not pretty obvious at first, but notice if we keep going down, what does it look like our number is approaching? So if you ask me, if our x is approaching 2.5, our y value looks like it could be approaching 27. So what's nice about this function is that we can just go ahead and plug in 2.5 for each value of x, And sure enough, our function of 2.5 does in fact equal 27. Now, of course, this function is a little bit easier, so we don't have to do this entire setup. But just remember, there are certain functions where you cannot just simply plug in the value that you're wanting to find the answer to. And so that's what makes limits so handy. So what are the key takeaways here? Well, remember, limit notation is all about as x approaches a number. And it could be any other variable as well. Of course, we could have alpha, y, n, whatever the variable in that situation requires. It can be for anything. And it's important that we distinguish it does not equal. As soon as you understand that limits are about approaching, the better position you'll be in future situations.